knows too much. Huh? There you go. And it's a 20-second delay. Usually I have to also make sure that I mute myself here for a second. Too much, huh? Yeah, correct. Now I'm muted from there. That's good. That works. And then I am going to share my screen with the introduction. The typical introduction is it will be 2 or 3 minutes of introduction, and then I'll pass it on to you, Mark. Okay.
Sounds good.
And we typically start right on the dot, right on that. And they all know that I give introductions, so many people start coming in around right on the time of that, and then yeah, it works pretty well. And as I mentioned to you, around 4 or 5, unfortunately, I will have to leave, but then Matthias will stick around as host and continue with the Q&A, no problem, yeah?
Sounds good.
So, then I'm also going to go ahead and start the recording. Also record it to the cloud. Okay, perfect. Yeah, and I'll try to, oh, yeah, I need to get ready the applause for you. I'm sure I remember that. That's something I always forget now because it's not part of the usual thing, but we need to do it often because otherwise it's so awkward. You finish the talk, it's like, thank you very much. Just like, here we try to do, because they don't have a clapping or things like that for some reason. I don't understand why not. But we will have, we typically have, we will add the clapping noise. They have the hands up thing, but the problem is that I say hands up everybody, hand hoch, yeah, in German, and then some forget to put it down, so they like asking questions. So yeah, it's all good. I think I'm going to mute really quick, okay. I think, and
that only helps if you have the participant window open.
Yeah, so well, the participants don't see the other participants, so they don't really the participant. Well, you know this. We're actually quite often participating, right? So they don't see each other. They can only ask Q&A. But so there's a lot of people, 35 countries really. I go by the official time is iPhone time, so it would be 1 more minute and then I'll start. Unfortunately, Karen is busy with her little monsters today because there's no Kita, so she will watch you later on live. Guys, on here. This is water, okay? Just people know me. You know, it's not happy hour yet. It will be after you. Okay, so let me start. So I would like to welcome all of you to the SPICE-SPIN+X seminar series. As many of you know, this is a seminar series joined between the Spin Phenomenon Interdisciplinary Center and the Collaborative Research Center SPIN+X between Kaiserslautern and Mainz, that is led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. Today we will celebrate Martina Schliemann's birthday. So this is Mark. You better do a good job for him. Yeah?
He's not here.
He's not here, but he's, you know, we're celebrating for him. As you know, we have line up every Wednesday talks. Next week, actually, the IEEE Magnetism Society Distinguished Lecturer, which is Matthias Chloe, will be giving the talk, and Axel Hoffman afterwards. And then some of you that are online will probably get invitations to go to the next one. Let me just say, okay, sorry, say a few words about Mark. Mark does not need introduction in our field. He has worked in this for a long time, and he graduated from Cornell University. I will not, the years there, you can read it and they can do the math. But he has almost as much as gray hair as I do, so similar is, and many awards. But he's known in the field as a very clear explaining the very hard concepts and bringing them to very good clarity that others have not achieved. And that's one thing that I love about it. And now he's going into an area that is very exciting, and his perspective is always something that we always look forward to hearing. So with that, I thank you all for attending, and I'm going to stop sharing. I'm going to ask Mark to go ahead and share your screen, and I'll mute myself and give you the floor. And we're looking forward to what you have to say. Go ahead and share your screen. Yeah.
Well, Jairo, thank you for raising the bar for me on the talk here and setting me up with high expectations. But thank you for the opportunity to talk about this work that I find very interesting and very exciting after doing other things for the last, well, you can all do the math. So the question is, why do you want to study the brain and figure out how you might use other devices to try to compute like the brain? So there's a lot of reasons that people have done. The sort of big picture is to understand how the brain works, maybe, or to develop machine consciousness, or to figure out how to do cognitive computing more efficiently. The thing about trying to address any of these questions requires that you are able to understand and communicate with people in wildly different fields. So if you want to understand how the brain works, you need to be able to talk to chemical biologists or neurologists or a whole wide variety of people. To develop machine consciousness, you need to talk to psychiatrists or psychologists and understand really what consciousness is. To do cognitive computing more efficiently, you need to be able to talk to engineers or computer architects. And of these possible ones, the ones that I find most easily I can fake is talking to engineers and computer architects. So I'm focusing on trying to figure out how to do cognitive computing more efficiently. So before I get started, I would like to figure out how to change slides, which is not happening. There we go. I would like to highlight the people whose work I'm going to be talking about today. So here are my colleagues in Gaithersburg working on hardware for artificial intelligence. And the work I'm going to talk about today is particularly the work of Matthew Daniels, Advet Madhavan, Philippe Talachian, and Alice Mizrahi. So why do we want to figure out how to compute like the brain? Well, when we originally developed computers, we developed them to do things that we're not good at, like doing high precision numerical calculations, like trying to figure out how to get a satellite up to observe Mars. It requires very high precision calculations, solutions of integral differential equations. And you can do those by pen and paper, but it takes a lot of time and a lot of effort. And so computers were developed to make it much easier to do these sorts of things. Today, we're asking computers to do more and more types of problems that aren't necessarily high precision numerical problems, but more like what the brain does well. Things like voice recognition, image recognition, those types of processes, driving a car. The human brain does those really well. The computer wasn't designed to do those. And so the hope is that if we try to do something like the brain does, make computers more like the brain, we may be able to do those things better. So what are some of the differences between traditional computers and the brain? Well, when traditional computers were developed, it was convenient to separate where information was stored from where information was processed. And so you have what's now called the von Neumann bottleneck. And that's because in the old days, the computers were mostly doing processing. There wasn't a lot of data being fed into them and out of them. It was mostly, like I said earlier, solutions of differential equations where it was a lot of processing and not much accessing of memory. But now if you're doing something like image recognition, there's a lot of data being passed back and forth between memory and the processing unit, and that is causing a significant slowdown to how well computers work. So the brain is organized very differently. It's organized so that all the processing and the information storage are co-located right where they need to be used. And so if you think about the incredible amounts of information that the brain is getting, like all the visual information, it's like continually doing image processing in real time, plus sensory input and auditory input. And that information comes in and it moves to the brain, and it's processed by very simple processors in place where the information needed to process it is stored. And so in the brain, the processing is done by neurons. And neurons take input from other neurons, typically in the form of spikes, action potentials. And then after a certain amount of input, they produce an action potential of their own that then gets communicated to a lot of other different neurons. The memory is provided largely by the synapses, which are the connections between neurons. And you can see by the ratio of synapses to neurons that there's a lot of these connections. And they determine how strongly the information coming out of one neuron is coupled into the input of another neuron. And so that's a very efficient way of doing processing of large amounts of data. Because computers are traditionally trying to do high precision calculations, they have a very rigid encoding. They have a binary representation of numbers where every bit counts. Every bit really matters to the solution. Everything is clocked and comes in rigid timing, and all the information's absolutely where it needs to be, exactly when it needs to be there. And a lot of work goes into enforcing this high level of precision in the processing that goes on. On the other hand, in the brain, the neurons are much more free-flowing. So a typical spike train from a neuron is shown up here at the top. And you can see it kind of looks random, and the information is sort of coming in the form of spikes every once in a while. But if you look at a whole collection of neurons down below, you can see that here along the vertical axis is the output of when spikes occur for individual neurons as a function of time. And you can see that this collection of 50 neurons is giving an oscillatory output. But each of those individual neurons, if you looked at it, you would have no idea that this oscillatory behavior was happening. So the information here is analog, it's stochastic, and there's no overall clock governing the behavior of the brain. So machine learning, artificial intelligence, has made a real dramatic breakthrough recently because neural networks, which are the simplest abstraction of the brain, have become quite efficient at solving a lot of these cognitive processes. And so the idea here is that you make a very simple neuron, and a neuron takes some inputs and then it produces an output. And rather than producing a series of spikes that comes out, it produces a number that tells you what rate it's producing spikes at. And then the synapses, which are the light blue arrows, which represent the connections between the neurons, take the output of each neuron and multiply it by the synaptic weight that couples one neuron to another. Then all of these inputs from one layer of neurons get multiplied by the synaptic weights. And if you think about this, this looks a lot like a matrix vector multiply. And then they get fed into the next layer of neurons. And what the neurons do with those inputs is they sum them all together and then operate them on them with a nonlinear function. And so the two things that make these deep neural networks very powerful are the fact that you have a lot of parameters to tune to adjust the output, and that's represented by the large number of synaptic weights, and the nonlinearity inherent in the neurons. If the neurons were strictly linear, you would just be doing no matter what you did, it would still be a linear transformation. And if the data wasn't separable in a useful way at the input, it wouldn't be at the output either. And so these nonlinear transformations play a really crucial role. So this revolution in machine learning has started out at the software level, but it's slowly getting spread throughout the whole computational stack. And so people originally wrote software programs that would do this type of analysis at the level of software on a laptop or a computer, and then bigger and bigger computers. But then as people realized that a lot of the time was being spent doing these matrix vector multiplies, they started using more specialized hardware like graphical processing units and tensor processing units, where you actually change the architecture of the computer to do those things more efficiently. And now there's a lot of effort where people are using specialty chips that actually go and change the way the information is encoded from a rate to actual spike trains. And there's a variety of chips that are implementing actual spiking processing. Now, as physicists, we're working down at the bottom of the computational stack, where we're interested in trying to incorporate new physical devices to try and enable more efficiency throughout the stack. And one of the things that I would like to convince all of you of is that when you do this, it's really important that you think across the whole computational stack and you talk to people who have expertise about the computational stack, because the properties that you want in a device to do computing depend on what you want to do with them. And what you want to do with them depends on what properties the devices have. And so it really takes a conversation across this stack to try to settle in on what the device is that you want to do a particular task that can take advantage of what those devices can do. So the type of devices that we're interested in here are magnetic tunnel junctions. And there's a number of reasons for this. One of the reasons is that magnetic tunnel junctions can do lots of different things. For example, they're mostly have been developed for non-volatile memory. And here's an example of magnetic random access memory devices that are integrated into a top state-of-the-art CMOS process. Now, this brings up another advantage of magnetic tunnel junctions, is that they're already a commercial scale technology. And so that means that if we can come up with a good idea how to take advantage of them, it will be very easy to get it implemented on a commercial scale because the devices are already available. And having non-volatile memory that can be embedded in the processing units is potentially a very useful thing that you could do to increase the efficiency of these computations. Now, down below in the lower right, I repeated these examples of neural spike trains. And if you look at those, there's two things that might come to mind. One is that if I look at this whole collection of neurons, I see strong oscillations. And so that makes me think, all right, if I had an oscillator, I might be able to do some really useful, efficient computing, because I might be able to replace all 50 of these neurons in the associated synapses with a single oscillator. And so spin-torque nano-oscillators are potentially a very efficient way of doing that. And about a month ago or so, Julie Grolier gave a talk on her efforts to actually implement spin-torque nano-oscillators in different forms of neuromorphic computing. And if that's intriguing to you, I encourage you to go back and look at the recorded version of her talk. What I'm going to focus on is another thing that you might take away from these images, which is the sort of random nature of the spike train coming out of an individual neuron, because that's reminiscent of the behavior of superparamagnetic tunnel junctions. So what are superparamagnetic tunnel junctions? Well, if I make a memory element, I want to have a high barrier between the two states. And so as you probably know, you're using the one configuration, parallel, which has a low resistance, and another configuration, the anti-parallel, which has a higher resistance to encode ones and zeros. And if you want to retain that information for a long time, you need to have a high barrier between those two. Now, as you start to lower that barrier, you can come up with memory that doesn't last so long. Why would you want to do that? Well, it's easier to change the state of that memory if you have a lower barrier. And so if you only need the information for a microsecond, you might be happy having something that's stable for a millisecond, like when you're using cache. And so you can make something much more efficient by lowering this barrier. And I understand that Intel is actually adopting this approach. Now, if you decrease that barrier even lower, say down to 7 times the thermal temperature, then the lifetime is on the order of microseconds. And you get behavior like you see down at the bottom, where the tunnel junction is switching between the high resistance and low resistance state in a completely random process. And so what we want to do is try to take advantage of this behavior and see if we can come up with efficient ways to compute based on that. And so there are a number of different ways that people, before I get to that, sorry, I got distracted by the next slide. Magnetic tunnel junctions can be controlled by the current. This is one of the things that makes them useful in applications, is that you don't need to be putting a magnetic field on them to control them. You can control them by passing a current through the device, through the spin transfer torque, or by passing a current in a heavy metal layer underneath them through a spin orbit torque. And this information over here to the left is what I have spent the last 30 years working on. No, last 20 years, sorry. But that's all I'm going to tell you about it today, except that when you put currents on in different directions, you preferentially stabilize one state over the other. And if you pass a large enough current, you can change the state to the more stable one. But if you change it when you're in the superparamagnetic state, you can change the relative amount of time that you're spending in each configuration. So here's a superparamagnetic tunnel junction, and I've balanced it so that with zero current going through it, it has equal probability of being in the parallel and the anti-parallel state. And so it's fluctuating like you see over here to the right. And it's got a rate of a particular amount and a mean resistance that's halfway between the parallel resistance and the anti-parallel resistance. And then when I start flowing current in either directions, I either stabilize the parallel state, as shown in red, or the anti-parallel state, as highlighted in blue. And so I'm either changing the average resistance to be close to the parallel resistance or close to the anti-parallel resistance. But in both cases, I'm decreasing the rate. And so these two curves give you two possible different ways of using these to compute. You can do probability computing, where you use the mean resistance as your signal, or you can use the transition rates as part of the signal. And I will focus in part of this talk on using the rate as what's being used for information processing. So there's a lot of effort going on in this field in using superparamagnetic tunnel junctions for doing computing. And the first was to generate true random numbers, because this is actually very hard to do in pure CMOS because you don't have random events. CMOS has been developed to be completely deterministic, and with something completely deterministic, it's hard to make something that's truly random. People do a very good job making pseudo-random number generators, but they aren't truly random, and they cost a lot of energy to use. And so you might think, okay, let's take one of these superparamagnetic tunnel junctions that's balanced, and we'll use that. Well, just using one isn't good enough, because if it's slightly out of balance, then you're favoring ones over zeros, and that makes it not useful as a random number generator. But then if you adjust the current through it to balance these things, then you don't have the configuration is uncorrelated, because as you are measuring it, you're adjusting the current, and that means that you're not really a truly random process. So the approach that people have taken is to take two of these and combine them in an XOR gate and then use the output for that. And so that makes something much more random, because the correlations in either are suppressed by this XOR process. But that's not good enough. You need to take two pairs of those and run them through an XOR gate. And actually, that still doesn't pass all of the different statistical tests. But if you take 8 of them and run them through the sequence of XOR gates, then this plot shows that you can actually satisfy the 180 different statistical tests that random number generators have to satisfy to establish that they are true random number generators. Another thing that there's been a lot of effort on is doing probabilistic computing. And you may have heard about the so-called p-bit, which is one of the most prominent approaches to doing this. And here I highlight a recent experimental implementation of this. And the idea here is that you set up a balance between the stochastic magnetic tunnel junction and a resistance that can be controlled by the input voltage on this transistor. And so that raises and lowers the voltage here depending on the state of the stochastic tunnel junction. That gets compared with a reference resistance and gives you an output that's either up or down depending on the state of the magnetic tunnel junction. And then by tuning this voltage, you change the probability that you're changing the current flowing through this device, and that changes the relative voltage here, and that tunes along this type of a curve here the different outputs, and this is giving you your nonlinear processing information function. And so people are doing a number of different tasks with that, and as an example, that paper reported factoring numbers using these types of approaches. The approach I'm going to focus on in this talk is rate coding. And so here the idea is that some neurons, at least, and so this is a neuron from some poor fish's eye, where the output of the neuron has been measured as a function of the angle that a particular stimulus has been at. And you see that this neuron is set to give a dominant response at a particular angle, and then it falls off as a function of angle. And that response curve or tuning curve looks a lot like the rate that you get out of a magnetic tunnel junction. And so we're going to use that as a way of processing information. So before we get to that, it's important to notice that these magnetic tunnel junctions are going to be embedded into complementary metal oxide semiconductor technology. And there are a number of good reasons why you might want to do that. And I have to confess that when I started working in this area 2 or 3 years ago, I was really ignorant about even freshman level electrical engineering along these lines. And so some of you are going to laugh at the basic level of this introduction, and some of you, like me, will say, oh, wow, that's really cool. And so the complementary in CMOS comes from the fact that you have 2 types of transistors. You have transistors with a p-doped well, which then have an n-type channel between the source and the drain. And you have transistors with a n-doped well that then have a p-type channel between the source and the drain. And so these are indicated up here in the sort of circuit design format. And for the purposes of this talk, that's all you're going to need to know. The properties that these 2 have that make this such a useful technology is that the NMOS transistors are off when the voltage applied to the gate is low, and on when the voltage applied to the gate is high. And the p-type transistors have the opposite type of behavior. Now, to see why that's useful, let's look at how you might make a simple inverter out of a CMOS circuitry. And so you have voltage sources, you have ground down here, and you have a voltage source up here that anything can tap into. And then in series between those 2, you have a PMOS transistor and an NMOS transistor. And the input controls the gate of both of those transistors. And so one thing that you notice is that one of those transistors is always off, so that you don't have a direct electrical connection between the high voltage and ground, so no currents flowing. You also notice, because the input's only connected to the gates, that there's no connection from the input to the output. So you don't have any current flowing along that path either. So this has some real advantages when you want to use these to do things. The fact that you're using the voltage to drive the output makes it possible that you can have fan out. If you use the energy of the input to produce the energy of the output, it becomes very difficult to do fan out, because that energy then needs to be divided along lots of different paths. But here, you're essentially coupling all those paths to the high voltage, and that makes it much easier to do fan out. One of the things that the brain has that makes it efficient is that it has a local energy source. And these voltage pins at high and ground that are available throughout the circuit, that is one of the things that makes this very efficient. And since you're only drawing current through these when you're switching, and the current that you're drawing turns out to just be the current needed to charge and discharge the gate transistors in the circuit, you can make these transistors operate at very low energies. And so a gate transition might be as low as 30 attajoules. And the final reason why you might want to incorporate CMOS in these types of devices is that we make a lot of CMOS. And that makes it a really cheap substrate to do things on, even if you're not taking advantage of the underlying circuitry. It's hard to imagine making as much of anything else as we do transistors, and that has led to very efficient processing of silicon at very small, high precision scales. Now, before I get to some specific examples on how we might use these, I first want to say, okay, CMOS is so wonderful. Why would you want to do anything else? Well, there's some things that CMOS doesn't do as efficiently as other things might. One is it's hard to make non-volatile memory. And so that might be a very easy way to implement magnetic tunnel junctions as local memory. Another thing that they don't do is plasticity. So if you think about the brain, the way it learns is it changes the synaptic weights. And the way it changes those synaptic weights is only based on the behavior of the upstream and the downstream neuron. And so that means you have this very local learning process that takes place. And this idea of plasticity and non-volatility is why there's a lot of work going on to try to use memristors, because they have both of those properties. Other things that are hard to do in CMOS are stochastic processes, as I described earlier. And you can make oscillators, but they take a lot of transistors, they take up a lot of area, they're not particularly power efficient. And so if you want to try to do that more efficiently, you might incorporate individual devices that are oscillators in their own rights. I find it useful to look at this plot of different energies relevant to these various processes. So if you start off with the biological processes, you notice that down at the bottom, ion channels are just functioning a factor of a few above room temperature. And so that makes these random processes, which means that if you want to do something deterministic with them, you need to use a lot of them. The other thing is that most of the energy in the brain is not spent in the actual synaptic events or neural spikes. It's actually in setting those up. And so the brain functions by maintaining a chemical potential difference for sodium and potassium inside the neurons and outside the neurons. And to do that, since it's non-equilibrium, you have to have pumps that are operating to pump these things out. And that's where most of the energy in the brain appears to be spent. And so these energies for neural spikes and synaptic events are largely the energy that it takes to set up those events rather than the energy actually used in those events. As you can see, for transistors, the gate transitions can be much lower energy than synaptic events and neural spikes. And so it's conceivable that you could mimic synaptic events and neural spikes with quite a few gate transitions and still have an energy efficient device. And so a lot of people are working along those lines. What I find interesting is going to the magnetic devices. If I look at the barrier for switching for MRAM, that's much lower than all of these other energies except for the ion channels. But the energy that it takes to switch an MRAM cell is orders of magnitude higher. And we don't have very energy efficient ways of doing that. And if we could develop those, that would make MRAM much more valuable as a potential device. So what I would like to do now is go into some specific examples. And I'll start off with one using population coding. And so this is some work that was done largely by Alice Mizrahi. She started off doing it as a graduate student with Julie Grolier and Damian Querlios. And then when she came and worked with me, she switched to a different aspect of the process. And so I'm going to talk about two different ways of using magnetic tunnel junctions. And the architecture that we're going to use is rate coding or population coding. And the information is going to be in different parts of the circuit is going to be in the transition rate of the superparamagnetic tunnel junctions or in binary weights stored in magnetic tunnel junctions. We'll use some particular CMOS circuitry, but I'll talk about in the next part of the talk. And so we're using the magnetic tunnel junctions in two different configurations. So let me remind you what those are. And so we'll have magnetic tunnel junctions with moderate barriers providing short-term memory, and we'll have superparamagnetic tunnel junctions with low barriers acting like spiking neurons. So here's the basic idea of population coding. So if I have one of those neurons that has a response like the tuning curve shown down at the bottom, And here I have a magnetic tunnel junction like that. And depending on where the stimulus is coming from, whether it's above or below, the output of the neuron follows this output path. Now, this is not an ideal way to process information, because if you're trying to spot predators, you get a lot of information if the predator is coming right at you. But if it's coming from above or below, you don't get a lot of information. It's coming much more slowly, and you're getting the same information whether it's above or below. And so a way around that is to have a population of neurons, each of which have their tuning curve optimized around a different angle. And that's illustrated down here at the bottom. And so then when you look at something coming at you from above or below, you get very different outputs from the population of neurons. And so what Alice did as part of her thesis work was to get some magnetic tunnel junctions that are supermagnetic and establish that you can do this type of population coding to provide a way of processing information. Because then when you take the output of all these neurons and multiply them by synaptic weights, you can very efficiently generate any sort of functional output that you would like. And so then, having established that, what she did was to do some modeling for how you might use this to control a robotic arm. And so here you have an eye that's sensing where an object is, a ball, for example. And then it sends its output to this set of superparamagnetic tunnel junctions, and they respond with these various output rates. Those get computed and then multiplied by the synaptic weights, which are stored in magnetic tunnel junctions, and then fed into another set of output superparamagnetic tunnel junctions to provide the controlling voltage for this motor that then tries to grab this ball. And it's possible for this type of a simple system to have a very simple learning rule that allows you to adjust these synaptic weights so that you can very effectively catch this ball as it's moving around. And so one of her colleagues then did a full circuit simulation for how you might actually implement this, including all the associated CMOS circuitry that you would have to have, and then compared that with a purely CMOS implementation and found that using the superparamagnetic tunnel junctions was very efficiently reduced the area and the energy that it took to operate this robotic control. And the key advantage that they observed was that these superparamagnetic tunnel junctions very efficiently do stochastic analog to digital conversion. So when Alice came to work with me, she focused on a different aspect of the problem, and that's, can we get some additional efficiency if, rather than storing the weights in very stable magnetic tunnel junctions, which require a lot of energy to switch, can we save anything by backing away and not having the synaptic rates stored in such a reliable manner? And the way to do that is to take advantage of continuous learning. Now, in many of these systems, the basic way they operate is you take an untrained network, you train it, and then you use it. Now, if something were to change or to go wrong, the system doesn't work so well. But if you have a system that's learning all the time, you start off training and then you continue to train it. Now, the energy invested in the training process goes down as the network gets better and better, because you have to change fewer and fewer things. But then if something happens, you can change the system and very quickly adapt to the changed system and continue to operate with very good efficiency. And so the example that we started with was to say, okay, let's take, say, the black curve where there's no loss in the transistors. And these are, of course, all simulations here. And we use this continuous training. How well does this robotic arm function as a function of the learning steps? And that's what's plotted in this black curve here. And then the idea was to make the transistors progressively worse and worse by lowering the barrier between the two different configurations. And as you do that, eventually things get really bad, but it turns out that you can go all the way down to a barrier of just 15 times KT for the particular timescales involved in this simulation and do just as well as you can without any loss. And so then the idea was, okay, can we optimize this? And so we're going to look at what happens as you change the number of neurons that you're using in this to control this robotic arm, and as you change the energy barrier. And so this blue curve here is a parametric curve of what the error was that you ultimately could train to as a function of the changing the energy barrier. And so as the energy barrier goes up, the error goes down because things are becoming more reliable, and the energy consumption goes up because the right current is proportional to the size of the barrier, and so the right energy goes like the barrier squared. Now you can repeat this for different numbers of neurons, and not surprisingly, as you have fewer neurons, you aren't as accurate, but you have much less energy, and as you add more neurons, the opposite happens. And then you can repeat this with arbitrary numbers of neurons and discover an optimum curve where you get the optimum power consumption as a function of the error that you want. And with that, you can, as a function of this error, you can predict what the optimum number of neurons was and what the optimum energy barrier was. So for example, if you were satisfied with 3% accuracy, that would tell you to use 54 neurons and an energy barrier of 12 KT. And so this is a way of showing that there are trade-offs between energy and accuracy, and depending on what your application is, different trade-offs might be important. And there may be some applications like face recognition for Facebook or your phone, that's not so important. You might be willing to settle for something that's much less accurate. On the other hand, for your face identification to unlock your phone, there you might want something that was much more accurate, and you want to pay a much higher energy cost for that kind of processing. Now I'd like to switch to a different approach. And here, this started out with the idea of a very general approach. Let's try to use superparamagnetic tunnel junctions to imitate these spike trains that you get from out of neurons and try to do some computing. And this was before we really understood how CMOS worked, because we thought if we made very sharp spikes, so we're mostly in the parallel state and just occasionally went up to the high state, that would be very efficient from an energy point of view, not realizing that that's inefficient because it's the transitions that matter. And so basically for each bit of information, we're making two transitions, and that's not very efficient. So as our processing evolved into how we can do this efficiently, we settled into the following type of an approach, which I'll outline here. So the way we're going to do it is to do stochastic computing, where we represent numbers by bit streams that are probabilistic. And so we can represent numbers between 0 and 1. And so we have a stream that goes on for some length, and it has some fraction of its time it's spent in the high state, and some fraction of its time it's spent in the low state. And it's not perfect. So here we're nominally encoding 0.2, and we're getting out 0.19 for 0.5. For this particular case, we're getting particularly bad. but we're designing a circuit to be resilient to that. So this makes a circuit that's resilient to noise or all sorts of things because we've designed it with this imprecision in hand. So how do you make a random bit stream in an energy efficient way? And so we quickly discovered that you can't do that by running a steady state current through the tunnel junction. That has a very high energy cost. And so what you really want to do is just read what the state is. And this is a particularly energy efficient circuit for reading the state of a magnetic tunnel junctions. And I don't want to go into much detail, but what's happening is you have these PMOS transistors up here and this NMOS transistors down here. And the ones with this purple flag are subject to a clock control. So they go alternate between high and low states. And when they're in the low state, this transistor is closed. These transistors are open. So the whole circuit settles into a high voltage. It just charges up all those capacitors. And then as the clock goes high, these turn off, this opens up. And what happens is all this charge wants to drain out down here. And it drains out through these two resistors. And depending on whether this state of the magnetic tunnel junction is higher or lower than this reference transistor, most of the current goes through one path or the other. And that goes and turns off some of the transistors up here so that these red levels and blue levels settle into an opposite state, either high or low, because one's connected to the high voltage and one is connected to the low voltage. And that gives a very efficient way of reading the state of the magnetic tunnel junction. All right, but that's not very satisfactory because if you only can output a probability of a half, you can't really do a lot of useful computing with that. But it turns out that because AND gates, which are only give you an output of a high level if both inputs are high, essentially multiply probabilities. And you can see that illustrated with this simple example over here. So then if we take two of these superparamagnetic tunnel junctions and couple them through an AND gate, we can get an output with a probability of 1/4. If we run that through an inverter, that gives us a probability of 3/4. And then this is a multiplexer, and depending on how this bit is set, that gives us an output here of either 1/4 or 3/4. We can take that output and AND it with another of these superparamagnetic tunnel junctions and get outputs of all the 8s, take those outputs and get outputs of all the 16ths, and then select which output we want here. And that allows us to get a bit stream of any of these probabilities between 0 and 1 by 16ths at a cost of only 10 femtojoules per bit, which is quite low and is much lower than any other implementation that we've seen. And it turns out that this is a factor of 2 lower than the energy it takes from doing a pure CMOS implementation, with the added benefit of being a true random number as opposed to a pseudo-random number that, like you get out of the CMOS implementations. And so you can very simply make synapses just by taking one of these programmable bit stream generators and an AND gate with the input from the downstream neuron that multiplies these two numbers and sends the output to the next neuron. And then it turns out that you can implement the neuron very effectively with a compound OR gate, because it turns out the OR gate adds the inputs, but it doesn't add the input. It does a nonlinear add of the inputs. And so these OR gates provide both functions of the neurons. They sum all the inputs and then operate on them with a nonlinear function. And so we have very efficient ways of implementing both the synapses and the neurons. And then we can put these together to construct a neural network. And so then the question was, how well do we do? Well, here up at the top, these are pre-existing CMOS implementations. And here is a set of different simulations that we did for different lengths of the stochastic bit stream. And so you can be more accurate for more energy with a long bit stream, and with a shorter bit stream, less energy, but less accuracy. These circuits were highly optimized to get to this point, and so we aren't reaching that accuracy. We believe that we could without too much more energy cost, but that's work that remains to be done. And these are tests on the same network structure using the same data set, so it is truly comparable. All right, so before I summarize, I would like to thank all my collaborators. The people in bold are the people who actually did all the work that I talked about today, but my understanding of neuromorphic computing and machine learning and using spintronic devices to do these sorts of things come out of discussions and other work with all of these different people, and I would like to thank all of them. So to finish up, I tried to convince you today that emulating different features of the brain can increase how well you can make a computer do the things that the brain does well. And we're trying to get computers to do that more and more. In order to do that, you really have to think across the computational stack and not just design a device and vacuum to do something, but you need to imagine how that's embedded in circuitry, how it's encoding information, and how the architecture can take advantage of what you're trying to do. In my belief, for room temperature computing, CMOS is likely to play an important role in any sort of computing technology in the rest of my lifetime. And so I would advocate for those of you who are trying to contribute to this field with different devices, figure out how you can augment CMOS, not try to replace it, because people have been trying to replace it for a long time and nobody has. Hopefully I convince you that magnetic tunnel junctions are a great choice for trying to do this. They're multifunctional. They already exist as an established technology. And I tried to do that by showing a series of different applications where we used a different architecture. The information was encoded in different ways, and we use these magnetic tunnel junctions in a variety of different ways. With that, I'd like to thank you for your attention.
Thank you very much. And then all of you guys in there, you can raise your hands to thank for the wonderful talk. And start maybe writing your questions. I haven't seen any questions being written directly here. Let me see, does somebody have, now you can lower your hands and then leave your hands up if you have some questions or comments yeah, there's a question here. Let me find out. So let me get to the person here and then go ahead and ask your question if you can unmute yourself. Hamid?
Yeah, okay.
Okay.
Sorry, can you hear me?
Yeah, yes, I can.
We can hear you.
Wonderful talk. My question is, it seems in brains, the transmission between neurons via synapse is kind of unidirectional, as far as I learned. Is there any way that in neuromorphic computing by magnetic tunnel junctions can mimic this unidirectional communication? Or is it necessary?
Well, so it depends on how you couple them. So if you're coupling them through an exchange interaction or electromagnetically, the coupling is going to be bidirectional. But if you couple them going through some CMOS circuitry, then that will be unidirectional.
I see. So exchange interaction is not unidirectional, but by CMOS it could be unidirectional.
Yes.
I see. Okay, thank you. Yeah.
Good afternoon. Good afternoon, Mark.
Hello?
Can you hear me?
Yes.
Good afternoon, sir. It's an excellent presentation. My doubt is, how does superparamagnetic junction is advantageous over ferromagnetic junction?
So a superparamagnetic tunnel junction is just a magnetic tunnel junction where you've changed the anisotropy so that the barrier between the two states is lower. And so you can have thermal fluctuations over the barrier. So they're identical structures. And so you could imagine, you know, if a an MRAM cell is designed to be elliptical, that creates an anisotropy barrier between those. And as you reduce the ellipticity, the barrier gets lower and lower. And if you make it purely circular, then the free layer magnetization is just kind of flopping around. And so a superparamagnetic tunnel junction is just somewhere in there where you have some barrier, but it's quite low.
Okay. Okay. Thank you, sir. Thank you.
Okay. I don't see any further questions, but I will have a question myself. So, okay, Matthias, go ahead and ask your question first.
Yeah, so thank Marx. I really appreciated this. In particular, the overview of the different energies of the operation. Can you just go to that slide where you showed how much energy it costs to go across the barrier versus the switching, and then compare that to the organic brain operation?
Let me see if I can figure out how to do that.
Yeah. Yes, exactly this one. So a neural spike is very expensive. And the brain doesn't spike that often. I mean, it's like kilohertz or something like that. Yep. What does that tell us?
Well, so, I mean, that's why you have lots of neurons, right? Because if you have an individual neuron that's not spiking that often, you can get a rapid spike train by having lots of neurons.
Okay, and many synapses connecting one neuron, so it goes from, okay. But does it mean, I mean, the question, do we understand what a single neural spike really means? Because if that is so expensive, it must generate quite a lot of effect, so to speak.
Well, I mean, I think the you have to look at it from the point of view of the neurochemistry of the brain, figuring out a way to do something. How does it communicate information, right? And these neural spikes are particularly efficient ways of doing that if what you have are chemicals, right? And so the reason it's so expensive is that it costs a lot of energy to pump sodium out and pump potassium back in, because you're pumping against chemical potential differences. And the actual energy involved in a spike is much lower, but it's just, that's the amount of energy.
Okay.
Right? And you know, and if you think about this, some of those neural spikes are going from one side of your brain to the other side of your brain. So they're going over a macroscopic distance.
Okay. Yeah. And what is ion channel energy? I'm not sure I understand what ion channel energy and synaptic event energy is. I understand what the spike is, but what are the other energies?
Okay, so when a neuron hits a synapse, it releases neurotransmitters. And so there's energy involved in the process of releasing these neurotransmitters that then act on the downstream neuron. And in order to capture these neurotransmitters and have them ready to be released, you have to pump various things around to get them captured within the synapse. And so the energy it takes to maintain that ability to communicate the information is primarily what dominates the synaptic event. The ion.
Go ahead.
The ion channels, that's how spikes propagate, right?
In the brain.
An ion channel opens in response to an electrical signal, and then say sodium rapidly flows in along the chemical potential gradient, potassium flows out. That generates the electrical action that then stimulates the next ion channels. And that's how information travels down an axon from one neuron to the next.
And that's very cheap. I mean, that's really KBT.
Yes.
Like, okay,
so Roberto, you have a further question? Your panelist now, so you can actually unmute yourself. So Roberto Raimondi, my good friend from Italy. Roberto, can you unmute yourself? You have a question? I had his hand up, so I'm not sure if you. So okay, I'll let him catch up with that. In the meantime, Adiam, you have also a question? You had your hand raised up?
Yeah. Can I ask the question?
Yeah, go ahead.
Okay. Thanks, Rajiv. Wonderful talk. And most of the I'm a magnetic man, so I don't understand about the brain part completely because I have never studied much of that. But still, if I can ask a big question, that you are using PMOS and NMOS on the same chip. So is it not difficult to fabricate this? Because in CMOS, is it very easy to do it? Or because for everything you need at least 2 to 3 devices more to do this one thing. So is it not increasing the number of devices? That's question one.
So this talk has pretty much saturated my knowledge about CMOS, except to say that yes, it's incredibly difficult, and that's why fabs are becoming so expensive to make. The cost to make a particular state-of-the-art fab is now approaching the GDP of moderate-sized countries. So yes, it is very hard. On the other hand, we can make them so well that we, in 2014, we made 10 to the 18th of them. And so we're very effective at making these transistors, and so that the cost per transistor is incredibly small. And the reason you want to use this pair of transistors is because that makes things energy efficient. And so if you tried to do something where you didn't have these pair of transistors turning the circuit off almost all the time, the circuits